Let's look at the history of the universe since the Big Bang and see how close we can get to the beginning. Some people think it's been a big anticlimax since the Big Bang. These are the cosmologists. Here's a timeline of cosmology to summarize the events that occurred in the history of this subject, which is really about 100 years old. It really starts with general relativity, Einstein's theory that explains gravity in an expanding universe. And the models of the expanding universe occur around that time from Friedman. The universe's expansion is finally measured in 1929 by Edwin Hubble. The ideas of the Big Bang nucleosynthesis, the creation of helium, and the prediction of the microwave background come in the late 1940s and early 1950s. In the 1960s, we find extremely distant objects called quasars, which are distant supermassive black holes at high redshift, and the microwave background radiation is discovered accidentally in 1964. The inflationary modification to the Big Bang model, its only major modification since it was developed, is in the early 1980s by Alan Guth and Andre Linde primarily. And then we have a series of beautiful larger and larger telescopes and surveys and increasingly detailed satellite observations of the microwave background. Cosmology is entering what's called its precision phase, where early measurements of parameters that were accurate to a factor of 2 have been replaced by precisions of 10% or even 1%, for instance, the flatness of the universe or the age of the universe. These are well-determined numbers at this point. And so we can trace back time as early as possible. The expansion history of the universe, an accelerating phase recently, the limit of vision of the Hubble Space Telescope and the James Webb to the formation era of galaxies and the dark ages that preceded the first stars and galaxies, the microwave background 400,000 years after the Big Bang, and there have been tests and confirmations of the Big Bang from the first few minutes by the light-heavy element abundances. We have a limit opposed by accelerators, which is the limit of our terrestrial physics, and that's our affirmation of the physics of the universe based on ground physics. And then there's tentative support from the microwaves of this incredible inflationary era before we reach what we consider the limit of our understanding, called the Planck era. So if we start there, the Planck era is defined as 10 to the minus 43 seconds after the Big Bang. It essentially marks the point at which we are unable to talk reasonably about the state of the universe, because at the moment we have no theory that can unify quantum mechanics, our theory of the very small, with general relativity, our theory of the very large. So we are powerless to describe what happened in this era. It's a veil over our knowledge. So that incredibly tiny fraction of a second is as far back as current science will allow us, until we have a theory, much hoped for by physicists, that will unify all these forces. And this is what it might look like. This is a unification diagram where the relative strength of the forces is shown as a function of temperature. And so we sit at the left hand of this diagram, where gravity is by far the weakest force. The electromagnetic and weak forces are in between, and the strong force that binds the nucleus of the atom is the strongest. The temperature at which the electromagnetic and weak forces merge is 10 to the 17 Kelvin. Incredible temperature, but that merger was demonstrated by accelerator experiments at CERN in the 1970s. Several Nobel Prizes were awarded for that work. So we have great confidence that at sufficiently high temperature, the distinct forces may be the same thing. The next threshold in this work is at a much higher temperature. You can see 10 to the minus 25 or 26 Kelvin, where the gut or grand unified theory force is. And we are unable to test that with terrestrial physics. The final supposition is that gravity can be linked to the other three forces in a uber force or super force that unifies everything, a true theory of everything. We're not there yet, but some people have ideas how it might be done. Meanwhile, we try and do the best we can with terrestrial physics to mimic the Big Bang, and that's really hard to do. Here's how early we can get an equivalent temperature in the universe history with terrestrial physics. You see a line drawn across at a temperature of 10 to the 17 Kelvin with the Large Hadron Collider. That's our biggest, most powerful accelerator. And if we read down on this chart of the universe temperature versus time since the Big Bang, we see that that corresponds to an incredibly short period of time, less than a trillionth of a second after the Big Bang. That's the limit of our ability to simulate the physics of the early universe. but it's led to incredible speculation. Will the Large Hadron Collider be able to create forms of matter that are unfamiliar to us now, even Big Bang itself or black holes? This is an issue that has concerned some people. And we move forward to the particle era. And this is the time when particles are as numerous as photons. After 10 to the minus 6, or a microsecond after the Big Bang, the universe is cooled to a temperature of 1 trillion degrees. And that's the point where finally we get radiation. Particles and antiparticles annihilate to form pure radiation, and a slight imbalance in the numbers of particles and antiparticles allow a small residue of matter to remain. And that imbalance probably emerges from the grand unified theories. We know that particles can be created and annihilated with antiparticles equally, but what we also see is a tiny imbalance in the nature of matter and antimatter early in the universe, which led to the annihilation of 10 billion and 1 particles with 10 billion antiparticles, leading to 10 billion photons and 1 particle equals mc squared. So particles and radiation are equally interchangeable. So the dominance of radiation over particles in the universe stems from physics in the very early universe. The nucleosynthesis era comes next. This is the first 3 minutes when we know that helium nuclei were created, and 1 part in 10 of the nuclei are turned from hydrogen to helium, which means 1/4 of the universe by mass is helium, predicted in the Big Bang and observed. The amounts of deuterium and helium-3 and lithium also agree with the Big Bang model. Then, from 3 minutes to 380,000 years, we have a hot plasma of hydrogen, helium nuclei, and electrons. The universe is opaque, like being inside a cloud. And 380,000 years just corresponds to a cooling and an expansion to a temperature where stable atoms could form and electrons combine with protons, and the universe becomes transparent. Then we end up in the era of atoms, the universe filled with atomic gas. Gravity has not had time to form anything yet, and so this is the cosmic dark ages. The universe is no longer glowing hot, it's cool, so it's dark, but gravity has not made stars or galaxies. But slowly, density enhancements in the gas and gravitational attraction of dark matter and normal matter is forming clouds that are slowly collapsing, creating the first stars and heavy elements in the universe. It's called first light. It's something that the James Webb Space Telescope was built to detect for the first time. And then on into the era of galaxies, the time from 1 billion years on when galaxies came into existence, and the current age of the universe, now a large, almost perfectly cold vacuum. We can summarize this from the Big Bang to the present day in this little animation.
Space itself exploded in a burst of radiant energy. In those first dazzling moments, the newborn universe began to expand and cool. Quarks combined into protons and neutrons, which later attracted electrons to form atoms, and the vast fog lifted. For hundreds of millions of years, the force of gravity slowly drew matter together into a gigantic web, the architecture of the cosmos. Two billion years passed. Clouds of gas and dust condensed like giant water drops along the cosmic strands and formed galaxies. Where the great ridges of matter crossed, galaxies came together in clusters.
I find the universe is more reassuring when it's narrated by Morgan Freeman. So here we are, the universe and us. We're pretty small. Here's the Earth, here's the solar system, the Milky Way, the galaxy we're in, and the universe as a whole. And in the final topic, we're going to look at speculative physics about the early universe, the idea of a multiverse. And that's the end of this topic.